Share my screen. Okay, everybody online can hear me and see me. You can't see me yet. Now you can see me. And we're recording. All right, so first of all, I had forgotten to put up on Blackboard the Dropbox of the homework assignment. I put it up, I don't know, 45 minutes ago or something like that. If you did not turn your assignment in yet, try to turn it in like right now because we're about to go over it. I made the actual due time like 11:30 so it wouldn't get flagged as late. If for some reason you don't have your laptop in front of me when you turn it in front of you right now or whatever, when you turn it in, just put a little note on there that, that you had it done on time or whatever. And then don't cheat off my solution I'm going to do today. That type of thing. All right. So let's keep trucking. I think today was what, binary search? Does that sound right? Is that what we did? Okie dokie. And this is what language? Java. Okie dokie. There we go. All right, so we were supposed to look at the algorithm for binary search, which is in the slides. And algorithm is back here, and I think I also, I think I maybe mentioned that you can find like tutorial videos and things like that. Okay, binary search requires your data initially be sorted, which is good because we already have a sorting algorithm for this. All right, the actual homework assignment is, so given the algorithm for binary search, implement a binary search inside of card parser that allows you to search for cards by its attack. All right, all of our sorts up to this point have sorted on its cost, right? So we need to sort on its attack first, then we can search within that using a binary search to find the attack a minion with the attack you're looking for in fewer steps is the idea. Sometimes a binary search is called a dictionary search. So the idea of it, the general idea is that, so you take a dictionary. Dictionary is already in alphabetical order, right? It's already sorted. So the way that a binary search would work is you're looking for the word cat, let's say. Well, as a human being, what do? You kind of flip through because you know it's in order and you find kind of roughly where cat would be, kind of open up to the first third, whatever, and then you zero in on it. But a generic algorithm like binary search would effectively say this. We're going to open to the middle of the dictionary. We're going to put our finger on the word that is right in the middle. We're going to say, is this the word we're looking for? No, let's say. Then we're going to say, okay, not the word we're looking for. Should it come before that word or after that word? So presumably I'm looking at like the L's or the M's or something like that in the middle of the dictionary. It should come before it. So if we want to be the aggressive version of this, we rip the dictionary in half. We throw the right side away because we know that if the answer is found, it's going to be found in that front half of it. Then what do? Rinse, lather, repeat. Go to the center of that. Pick the word. Is that the one we're looking for? If yes, we're done. If no, should have come before or after that. Go to whichever side, move to the middle, pick the word, so on and so forth. All right, that makes sense. You do that until the middle, left, and right are the same. You don't have anywhere else to check. That's when you can get I didn't find, if we search for a minion with an attack of -7, we're probably going to come up short, right? We're not going to find one with an attack. I guess I'm presuming that's the case, but it's probably a true statement. All right, so we have two things we need to do here. We need to adjust our sorting to, instead of sorting on cost, it sorts on attack. Okay, so let's do that first. Then we'll write a binary search. Now, sorting on cost on attack instead of cost is going to be a fairly quick little change. We'll just pick one of our sorts. Let's do our insertion sort. I'm just going to copy this and then we'll. Okay, so we'll say insertion sort lowest attack to highest attack. All right, changing the name because this guy's going to sort it a little differently than before. Still do the same thing we did before, but now what we're going to do, instead of getting the cost, we need to get the attack. So we need to expose that from our Hearthstone card. So attack is a private variable. When we looked at cost, we created a get cost function that exposed it. I'm going to go ahead and do the same thing for our attack. We can just write it by hand, or as a reminder, you can right click, go to source, go to generate getters and setters. And then for attack, I can just add a get attack. And that'll just write the tiny little method for you. All right, so remember, a getter like this is just the method that gives us public access, read-only public access to a private field. Okay, nothing special, it's just a method. Normal plain Jane method, we just kind of categorize this guy as, oh, this is a getter because it allows us to get at a private field. So now we have get attack. So we can come in here now, and instead of comparing the cost, we can compare the attacks. And do our swaps and stuff based on that. Okay, and if we want to see what this looks like, we can go into driver. We'll go ahead and call our new. So we have insertion sort lowest attack to highest attack. And then we'll show our minions, and we should see whoever the strongest brawler is at the bottom of our list. Let's go ahead and run this. All right, this dude has an attack of 30, the ancient one. He only has a cost of 9. There's got to be a catch with him. There's some cards on there that like they can only attack if like some weird condition is met. So he might just be kind of like a really tough guy that can't do anything. But in any case, we see that these guys are sorted. Here's a attack of 8, so on and so forth. Here's an attack of 5. Seems to be sorted in smallest attack to highest attack. All right, so now we're sorting our data in the correct way. All right, now we can go ahead and write our binary search, because remember, binary search requires that we have sorted data. More specifically for us here, it requires that we have data that's sorted in the way in which we are looking. So like I used the dictionary as an example a few minutes ago, right? Well, a dictionary is already in alphabetical order, and we know if one word comes before or after another word. So it's already sorted in the way that we're comparing words. Well, in this case, I needed to sort it on attack because I'm going to be searching for attacks. All right. Sorting it on cost and then searching for doing a binary search on attack is not going to give you very good results, right? You may have gotten the correct answer. It just may have gotten to that in a weird roundabout way, because if you had it sorted on cost, I can maybe say that the lower cost cards have lower attacks and the higher cost cards tend to have higher attacks. That's not guaranteed, but it's probably a truth. Okay, it's probably a truth. But the idea is that your binary search on that might, let's say, accidentally give you a result. But because you weren't searching it based on correctly sorted data, sorting it on attack, you're not guaranteed to get the most efficient result or even a correct result. Okay, so we are sorting it on attack first. Now let's go ahead and let's write our binary search. So I'll go into card parser and we'll do public. Now we're going to go ahead and return a card. So it's going to return a Hearthstone card. And we'll call this guy binary search on attack. And we're going to search for the first card that we find that has that attack. Something like that. All right. So we'll say this guy returns the first card it finds with an attack of attack, or null if no card was found. Because it is possible, like I said a few minutes ago, if we search for an attack of -7, probably not going to get a result. All right. So first thing we need to make sure happens here is we need to make sure that our data is sorted on lowest attack to highest attack. So I could rely on the user to do that externally, right? I can just say, look, before you call this function, sort the stuff. Or I can just ensure that it's sorted by inside here calling insertion sort lowest attack to highest attack. I could just make the first line of this guy, make sure it's sorted. Right, so the first thing binary search will do is it'll make sure the data is sorted, and then we'll actually do the binary search. All right, so the binary search requires us to calculate the middle of the collection. Okay, so that means from our current starting point to our current ending point, what's the middle? Well, initially, the current starting point is going to be the beginning of our full array, right? Bucket 0. So int cur start will equal 0. And the current ending point, int cur end, is going to be equal to this dot the minions dot size -1. That's the last legal bucket in there. Okay. Then we're going to go ahead and we're going to say we're going to keep checking until cur start is greater than cur end. Right? Because the idea is that each time through, cur start should change depending on which half we're looking at. And as soon as those guys crisscross, we've checked everywhere we need to check. We really should say greater than or equal to, because we know the very last time will be when everything aligns and cur begin, cur end, and middle are all the same thing. That's our last hope for finding this, right? Okay, so because we don't know the nature of how middle is going to be solved yet, we're going to say, you know what, we're going to keep checking as long as, so while, I'll actually write it in words first, keep checking as long as the start is less than or equal to the end. So while cur start is less than or equal to cur end, we're going to go ahead and do our check. Make sense? So now what do? We need to calculate middle. So I can define middle ahead of time here, just say int middle. And then inside here, I can say middle is going to be equal to. So now we need to figure out how do we calculate the position that is the middle of our collection. Now, this is part of the trick of binary search. Because we might say, well, if beginning is 0 and the ending is 30, well, then 30 divided by 2 is 15. That's the middle, right? Well, what if the beginning is 15 and the ending is 30? 30 divided by 2 is 15. Is that the middle of that collection? 15 to 30 is the middle 15? Or is the middle somewhere in here? 22 or something like that, right? Okay. So the algorithm for calculating middle isn't the end divided by 2. It's the end plus the begin divided by 2. So if I had 15 to 30, 30 plus 15 is 45. 45 divided by 2 is 22. That's the middle. All right, makes sense? So to calculate our middle, we're going to say cur begin, or cur start, plus cur end divided by 2. And this is integer division. So the decimal point truncates. So a 22.5, for example, would become a 22. That's what truncates means, just cuts off the decimal point, doesn't try to do any rounding or anything. The reality is, even if it did do rounding, that wouldn't matter for this algorithm, as long as we're always calculating the middle the same way. Effectively, what we don't want to do is we don't want to skip buckets, right? So even if the middle is a little bit short of the middle or a little bit beyond the middle, doesn't matter, because we're certainly going to have collections that have uneven number of elements, right? Okay, so sometimes we won't get the exact middle, we'll get the middle-ish. But as long as we're calculating the middle-ish the same every single time, we'll be in good shape. All right, so as long as cur start is less than or equal to cur end, we're going to calculate our middle. Then we're going to ask the question, did I find my answer? That is, did I find a card whose attack is equal to attack? If this dot the minions dot get bucket middle dot get attack is equivalent to the attack I was looking for. That's what that asks, right? I go to my collection, this dot the minions, I get the Hearthstone card that lives at bucket middle. I ask that card, what's your attack? And I say, is that attack the same as the attack I was looking for? If it is, I'll go ahead and return this dot the minions dot get middle. That's the card I'll return. Now, I'm done. My loop will end because return makes the function immediately end. But if I didn't find it, now I need to ask the question. So we'll say else. If I want to know, is the attack I'm looking for, is it less than the current guy, or is it greater than the current guy? Now, before we go any farther here, wouldn't we admit that this ninja move we're doing right here is fairly complex? We're kind of stringing a bunch of things together, right? I mean, it's like, you know, got the minions, get a certain bucket, then get that guy's attack. We're kind of doing a bunch of things, and we don't want to have to keep writing that over and over again. So what I'm going to do is I'm going to create a Hearthstone card, maybe called temp here. And what we'll do is we'll set temp equal to this guy. Okay, so that's our card. So then we'll say if temp's attack is equal to attack, return this. Else if temp get attack, if that guy is less than, actually, let's ask it this way. If the attack we're looking for is less than temp's attack, then we know that if there is a minion that has that attack, it must be to the left of this. And if it's to the left, what do? We adjust cur end. So cur end will equal middle minus 1. Else, if it wasn't equal to the attack and it wasn't less than the attack, it must be greater than the attack. And if it's greater than the attack, we adjust cur begin is equal to middle plus 1. All right, so now our new range of values is a cur begin, cur start. So our new range of values has shifted. We started off looking at the whole collection, then we're looking at either the front half or the second half, depending on whether the value we found should become before or after. All right, so we'll adjust cur end, we'll adjust cur start. It'll loop back up as long as those guys haven't crisscrossed each other. So as long as cur start is less than or equal to cur end, as long as this basically says, as long as there's still a place to check. Let's do it again. And what do? We calculate our new middle. Then we get the card at that new middle. Then we start asking questions about that guy. If we survive this while loop, that means we never got into a situation where the attack we're looking for is equal to the attack we were searching for. So generically, I might say we're going to return null. So null is nothingness. That is the value of a card that has nothing in it. And we're going to see maybe the problem with this here in a second. Okay, so there's my binary search on attack. Now let's go ahead and test this guy. So we'll go ahead and say CP binary search on attack, and let's look at for an attack of 5. And we'll store that inside of answer, and then we'll say answer.display. All right, so presumably we're going to get a card that has an attack of 5. I think I saw one that we did have a card that was an attack of 5. When we call binary search on attack, what's it going to do? It's going to first sort on attack. It'll do that for us. Then it'll apply that binary search algorithm to, or the dictionary search, to finding the first card it bumps into that has an attack of 5. So there's our Emperor Thorsan, cost 6, attack 5, defense 5. It's not that great of a card unless he has some extra abilities. Okay. So there's an, go ahead. Say this one more time. I must have it inside of the constructor for card parser. Yeah, here I'm printing out stuff inside of my constructor when I'm building up that collection. So this is the constructor for card parser. So it shouldn't show anything now. That was when we were looking at, what were the various fields that were available to us so we can decide what we wanted to keep and what we didn't want to keep and that kind of stuff. All right, so this seems to work for values that make sense. But what if I put in a -3? I'm guessing that there isn't a card in there with an attack of -3. I guess it's possible, but I've never seen a card with a negative attack value. So that means that the value that's going to come out of here is a null value. So answer is a variable that will hold nothing. What happens if I ask nothing to call its display method? Yeah, not good things, right? Not good things. So we'll go ahead and run this. And it'll scream, it'll say null pointer exception. You tried to call a display function on nothingness. Don't do that. Okay. Now we've looked at exceptions in here. Try and catches. Have we done that at all? Okay. So what's my workaround? So let's look at different ways we can approach this. So first of all, any question on the binary search algorithm? I can go ahead and push that. Actually, let me give you a version of it that won't give you an error. So updated for binary search solution. What was this, homework 9? Homework 10? Okay, so that guy's up there now. So what can I do with this? So again, we'll have our error here, right? What can I do to fix this? Well, I can only display if it's not null. So I can wrap this in an if statement. I can say if answer.display, I'm sorry, if answer is not equal to null, then call answer.display. Else, I can do like a system.out.println no card found. Something like that. And now when I run it, I'll get the no card found thing here. Go ahead. Yep. So that's where we're going. So this is one workaround, right? Okay. So what's the next thing we can do? Well, we're going to say that all programs begin and end with main. So we want our main to look pretty clean. So while this logic makes some sense, we probably want to kind of suck that into our class. I'm not sure if card parser belongs as the home for all these things, but that's where we're putting them right now. At the very least, we're going to get it out of main. So we're going to go into card parser. And we're just going to write a function here called public void display card with attack. This guy will take in an int attack. And then what we're going to do is we're going to say Hearthstone card answer is equal to this dot binary search on attack, whatever the attack was. Then we can ask the question, if answer is not equal to null, answer.display, else system.out.println no card with an attack found. All right, so we'll put that logic into this display card with attack thing. So now back here in driver, we can say CP display card with attack, pass it a number, and this will go and find something that has an attack of 5. If I put in my -2, it'll show me no card with attack of -2 found. So on and so forth. So this makes main look a lot cleaner, even though the identical logic has been pulled inside of this class. This is that whole object-oriented programming thing where we like to see, we don't want to see the wires, even though we know the wires are there. Okay. Now we could probably make an argument that all this stuff probably shouldn't go inside of card parser. Maybe we should have another class that kind of has our, utilities or something, like card utilities or something. But for right now, we can just put everything in card parser. We're getting good enough practice with that. But let's look at some other options we can do with this. So right now, and we'll go ahead and keep the logic inside a card parser, but I'm going to add it to the notes here. I'll call this null values. If we try to call methods or fields on null values, we will get a null pointer exception. This effectively means that we are asking nothing for some information, which doesn't make any sense, right? Doesn't make sense in real life, wouldn't make sense in a computer program. Okay? You can't go up to nothing and ask it for a soda. You're not going to get a soda. Okay, people, you're just literally talking to the wall at that point. All right, so what are some ways we can handle this? How do we deal with this? Well, we can wrap the logic in an if statement to ensure we don't try to ask a null value for stuff. We can also use Java's exception handling to accomplish this. Now, we've seen the exception handling stuff just a few minutes ago when we saw null pointer exception. So Java itself is using its exception handling where it's saying, hey, here's something that went wrong. This is my way of telling you. Now, for us, it just jumped to the screen. Okay. Now, let me show you an alternative here. So I'm going to go back into driver, and hopefully I can just reverse this. So I went ahead and put that logic back in here. We're calling our binary search directly. All right, but I want to get this this null stuff out of here. Okay, so this is the condition that'll give us our null pointer exception, right? So we're already getting this guy to throw us a null pointer exception because we tried to ask nothing to display. What we can do is something called a try catch. So we can say, I want to try to do some of this stuff. And then I can say, I'm going to catch an exception that might happen. Something like that. So, well, this looks fairly similar to our if statement. Before we were saying, if this guy is null, then print out no card found, otherwise ask it to display itself. Now we're saying, look, I'm going to try to do this. We could put as many lines in here as we want. I'm going to try to do all this stuff. And if something goes wrong, now we can look for specific things that have gone wrong. We can have multiple catches with a single try. So let's say inside of this single try, we can have a null pointer exception, but we can also have an array index out of bounds exception. Two things we've seen, right? You try to access bucket -4 of the minions, that's an array index out of bounds exception. If I try to do system.out.println, do we have the ability to get the minions? Yeah. Well, I want to show it. Go into card parser. I'm going to add the ability. So I'll go into source, generate getters and setters. I'm going to give us the ability to get the minions. So now out here in driver, I can go ahead and say system.out.println cp.get the minions.get bucket -4. And then for right now, I'm going to show you, I'm going to do print stack trace, I think. There we go. So that'll print out the error message that we would have saw otherwise. But this is me, and I'm doing it this way instead of removing the try, which would throw the error. All right, so the first thing I'm going to do is I'm going to try to access bucket -4 of our array of minions. That's going to be problematic. We're going to get an array index out of bounds exception from that guy. And we'll print out, we'll see array index out of bounds exception. There's my index out of bounds exception. Now, if I switch this back over to, let's say, just get bucket 2. It's going to show me the address of a card, but then it's going to show me my null pointer exception. This was the card found at bucket 2. No problem. So this line's fine now, right? But then when I tried to get call display on a null value, I got my null pointer exception. So both of these lines are potentially problematic, right? Under different situations. So what I'm doing here is I'm catching a generic exception, kind of a lazy way of doing it. I'm saying, look, I don't care what bad thing goes wrong inside of this try. I just want to recover from it and say something bad happened or whatever instead of the program crashing. But you can be more granular than that. You can say, look, I'm interested specifically in an index out of bounds exception. And what we'll do here is we'll say, don't walk off the end of the array list in this case. We'll also catch a null pointer exception. And this is where we'll say like card not found or something like that. All right, so now we got our card not found because the null pointer exception got caught here. If instead I do a -2 up there, we get our don't walk off the end of the array list. All right, so we're catching the various kinds of errors we could have gotten in there. We have that level of control if we want to. Does that make some sense? All right, now so let me do this. I'm just gonna copy those 2 lines. I'll put them right here. I'll comment all this out. So that's what it looks like if we're doing it from this side. We're saying, look, nobody's policing me. Nobody's saying that there could be a problem here. I just happen to know there could be an issue, so I'm going to wrap it in a try catch. Fine. But what if we knew when we wrote a function that there was a possibility that it was going to return a null value? Might it make sense for us to say, I don't want to return a null value. If I have to return a null value, I wasn't able to do my job. And I want to let them know that I couldn't do my job. I want them to be forced to become aware that I couldn't find the card they were looking for. Make sense? So what I can do here is inside of card parser, I'm going to do it on the binary search thing. We can claim that this guy throws an exception. He's going to throw an exception. Really, he's going to throw in this case. So again, I use exception generically. There's a hierarchy of objects, exception objects in Java. So you have the top level one, you have object, then you have a more specialized thing called an exception, then you have an even more specialized thing called like a null pointer exception. There's 3 levels there. So a null pointer exception is an exception, which is an object. All right, so I can just say I'm throwing any kind of exception from within here, you got to deal with it. Or I can specifically say I'm going to throw a null pointer exception. So then down here, instead of returning null, we're going to say, look, if I can't return a real value, I'm not going to return anything. Well, Java's going to scream at me right now. Java's going to say, look, you told me you were going to return a value. You got to return a value. You told me you were going to. Make sense? So we either have to return a value or we have to notify Java something went wrong. So down here, we'll say we want to throw a new null pointer exception. I couldn't find a card with attack, something like that. All right, so this guy is going to throw a null pointer exception with this message in it. And this method has advertised that it throws a null pointer exception, which then means when I go back out here to driver, let's see, use binary search on attack. Why isn't this guy yelling at me? He should be yelling at me. So there's my null pointer exception that says I couldn't find the card with that attack, so that part worked. And I advertised that I was throwing an exception. The way this should work is if a function advertises that it throws an exception, whoever's calling the function is now in charge of handling that exception. So my understanding is that out here in driver, this should be giving me an error because it's saying this guy might have an exception associated with it. I wonder if this is because it's in main. Let me just try something here in. We'll do it at the end of our constructor after the thing's been built. This dot. No. It's not doing it. Am I using the right keyword? Throws? This guy throws a null pointer exception. Oh, I know what the problem is. Null pointer exceptions are actually what are called runtime exceptions. So let me cheat and just say I'm going to throw an exception. I'll throw an exception. Couldn't find the card. Now out here in driver, he's not happy. He's just saying unhandled exception, type exception. Null pointer exceptions belong to because now you have object exception and then you have a runtime exception as well. So a runtime exception is something that Java says, you don't have to deal with me if you don't want to. I'm something that happens at runtime, just so you know. It's also our mechanism for throwing our own errors without forcing somebody else to do this. So we'll talk about runtime here in a second. So it's saying, look, this function throws an exception. We are now self-policing ourselves. We're saying you have to deal with this exception. So now we effectively have to put this try catch in here. So we have to put this try catch in here because if we don't, it's going to say, you know what? This guy here potentially throws an exception. And since it potentially throws an exception, you have to deal with it. Now, we could still cheat. and do this. So right now it's yelling at me and says, hey, this guy potentially throws an exception. You have to handle it. It's your problem. And I'll say, no problem. I'll just pass the buck. You're going to give me a hot potato? I'll hand it to the next guy up. So you're going to throw me an exception? I'll take the super lazy way out and say, I don't want to write a try catch. Main, there you go. This is your exception to deal with. All right. So it's kind of interesting. We can be lazy even as programmers, right? Somebody gives you an exception, you don't want to handle it, or you say, look, fine. We could have like, maybe let's say it's like a file not found exception. You try to open up a file called, mystuff.dat. And you're like, look, I know the file's there. It's there. I wrote it, put it there. I'm not going to wrap this with a try catch, making my code kind of more difficult to read, let's say, when I know it's there. This isn't something that's actually going to happen. So I'll just put a catch-all throws exception up here to just make it so I don't have to deal with it. That's not an unreasonable thing to say. All right, that makes some sense? All right, so let me just add to the notes. So no homework for Friday. But we're going to, I want to start here on Friday. Start here Friday. We're going to talk about runtime exceptions. All right, questions, comments, concerns, bribes. I'll see everybody on Friday.